Hello friends, welcome to our today's online session in chemistry. In today's session, we will see trends in atomic properties of first transition series. First we see atomic and ionic radii. What is meant by atomic radii? One half of the internuclear distance between two adjacent atoms or ions is called as atomic or ionic radii. Atomic and ionic radii of transition series decreases gradually from left to right. As we move from the transition series from left to right, the nuclear charge increases by 1 unit at a time. The last filled electron enters in a penultimate n-1 d subshell. Penultimate means second last shell. That is n-1 d subshell. D orbital in atoms are less penetrating or more diffuse. Therefore, d electron offers small screening effect. Screening effect means there is a reduction of attractive force between nucleus and the valency electron due to the presence of electrons in the inner shells. Screening effect increases with increase in the number of electrons in the penultimate shell. As the number of electrons in the penultimate shell increases, the screening effect increases. Therefore, due to this screening effect increases with increasing the number of electrons in the penultimate shell. As a result of this, effective nuclear charge also increases as the atomic number increases along the transition series from left to right. You can see in this graph the atomic radii decreases from left to right as the atomic number increases and screening effect also increases. Ionic radii show the same trend as the atomic radii. Then next to this is variation in ionization enthalpies of transition elements. The ionization enthalpy are the energy required to remove an electron from its atom in its ground state. The ionization enthalpies of transition elements are intermediate between those of S block and P block elements. This is because the nuclear charge and atomic radii of transition element lie between S block and P block elements. As the atomic number of transition elements increases along the period and along the group, the first ionization enthalpy increases. In the transition elements, the last electron enters into n-1 d orbitals, and this shields the valency electron from the nuclear attraction. This gives rise to screening effect of n-1 d electrons. Due to this screening effect of n-1 d electrons, the ionization enthalpies increases slowly, and this increase is not very regular. The first ionization enthalpies of third transition series elements are higher than those of the elements of first and second transition series. This is because in third series, the elements having a 4f orbitals are filled. The 4f orbitals, due to their diffuse shape, exhibits poor screening effect. Hence, the valency electron experience greater nuclear attraction and greater amount of energy is required to ionize the elements of the third transition series. Therefore, the ionization enthalpies of third transition series elements are much higher than those of the first and second transition series. Then next to this is metallic character. All the transition elements are metals. They are hard, malleable, ductile. They having a high tensile strength. They having high melting points and boiling points. Their metallic character is due to vacant or partially filled n-1 d orbitals and they involve both metallic and covalent bonding. The strength of metallic bond depends upon the number of unpaired electrons. It increases up to middle, that is up to n-1 d5. Hence, accordingly, melting point and boiling point also increases up to n-1 d5 configuration. After n-1 d5 configuration, the electrons start pairing. Hence, the metallic strength, melting points and boiling point decreases with increasing atomic numbers. Means up to chromium, the melting point and boiling point increases from scandium to chromium. After chromium, the number of unpaired electron goes on decreasing due to pairing of electrons. Hence, metallic character, melting point and boiling point decreases from manganese to copper. Zinc having all electrons are paired. Hence, it is a soft and having a low melting and boiling points. Then next to this is color of transition metal ions and compounds. A substance appears colored if it absorbs a portion of visible light. The color depends upon the wavelength of absorption in the visible region of electromagnetic radiation. The ionic and covalent compounds formed by the transition elements are colored. Transition elements contains unpaired electrons in their d orbitals. Transition elements contains unpaired electrons in their d orbitals. When the atoms are free or isolated, the 5d orbitals are degenerate. Means they are having a same energy, but in compounds or in presence of anions or complexing ligands, the degeneracy is lost. These 5d orbitals, dxy, dyz, dxz, dx square minus y square and dz square. These 5d orbitals are split into two groups. One group of d orbital having a lower energy and consist of three orbitals. They are dxy, dyz and dxz. These orbitals are called as T2g orbitals. The second group of d orbitals having a higher energy and consist of two orbitals, dx square minus y square and dz square, and they are called as Eg orbitals. The energy difference, that is a delta E, between these two sets of d orbital is called as crystal field splitting energy, that is CFSE. This delta E having a very small value, and this equal to the energy of electromagnetic radiation in the visible region, that is delta E is equal to h nu, which is equal to the energy of electromagnetic radiation in the visible region. There arises a transition of one or more unpaired electron from T2g orbital to Eg orbital due to the absorption of radiation in the visible region. When the electrons from a higher energy level returns back to the lower energy level, that is T2g, it transmits the light that is complementary in color to color of radiation absorbed. This imparts a characteristic color to the compound or a metal. There is a color wheel is given. There are the complementary colors are shown opposite to these colors. If there is the red light is absorbed, then the transmitted light contains excess of other colors in the spectrum in a particular green, and the compound appears as a green. The ions having a no unpaired electrons are colorless. For example, copper plus ion having a 3d10 electronic configuration. They are having a completely filled orbitals, no unpaired electron. Titanium 4 plus ion, 3d 0. There is a no d electrons. Means the ions having a no unpaired electrons are colorless. Then the cobalt chloride. One example is a cobalt chloride is dissolved in water. It forms a pink solution. Cobalt 2 plus ions dissolved into water. Then hexa aqua cobalt 2 plus, which having a pink colored solution and octahedral geometry. But when this solution is treated with concentrated hydrochloric acid, it turns into deep blue colored solution. This change is due to the formation of another complex, that is cobalt chloride 2 minus complex, COCl4 2 minus, which having a tetrahedral structure. Thus, the color of the transition metal ions are due to the presence of unpaired d electrons. Then d-d transition, nature of ligands attached to the metal ion and geometry of the complex formed by the metal ions.